Alright, in this video, we study how to make a new function or a map by combining or rather composing existing maps. And how we combine or compose maps can make a new algebra of functions or maps. So let's start. Okay, first let's define map composition or map or function composition. So suppose we have two maps, F, that is from A to B, A and B are sets, and another map, G, whose domain is B and codomain is C, let's say. Okay, note that the codomain of F is the same as the domain of G. Okay, then we define the composition of F and G, which we write like G circle F, which we usually read G after F. Okay, so this is a new function or new map that goes from the domain A to the codomain C. And the rule of assignments of elements of C to elements of A is given as follows. That is, so this is a new map, right? So each element in A, this is the value of G after F of X is given by G of F of X. So it's very simple. First, we apply the map F to X. Then to the result of that, we apply the map G. So this is called composition of F and G. Okay, and graphically we can write like this. So A to B. So F maps the set A to set B, and the map G maps set B to set C. By composing this, we go from A to C. So this is G after F. Okay, so we first go from here to here, then from here to here. The result is A to C. So this kind of diagram is called commutative diagram. So that means the path from A to C, there are two paths, right? From here and from here to here. But either way, we get the same result for each element of X in A. So each element in X, what we have here is G after F of X. That is equal to, so first, if we apply this, we get F of X. Then to that, we apply G and we get G of F of X. So this is the definition of composition, and that's what this diagram represents. As you can see here, map composition can be done only when the codomain of one map is the same as the domain of the second map. Okay. Otherwise, we can't combine them. So, for example, we can define F after G after F here like this because the codomain of F is B and the domain of G is B, and they are the same, right? However, we cannot, for these functions or these maps, we cannot do F after G because it doesn't make sense. So G sends elements of B to C, but F takes elements of A, not the elements of C. So we cannot compose like this. It's impossible for this case. Okay, therefore, we can say that map composition is not commutative. So G after F is not equal to F after G in general. And another note, some authors or some mathematicians or computer scientists maybe, they prefer to write f then g instead of g after f. So this maybe may mean the same thing as g after f, right? This is more like a program, computer program. So first we apply f, then to the result of that we apply g. So this may look more natural to some people, but in mathematics we usually use this notation. But it just depends on the convention we are adopting. So so whether we use this or that is not so important, as long as we are clear what we are doing. Okay. Let's see one example. Let's say we have a map function f from the set of integers to set of integers defined by f of x as, let's say, x minus 1. And another function, g, from the set of integers to the set of non-negative integers, that is natural numbers and 0, defined by, let's say, g of x as, let's say, x squared. Okay, so then we can compose f and g. So g after f is a function from this integer to this non-negative integers, and that is defined as g after f is defined as g of f of x. That is, so first apply f of x, then we have this, so f x minus 1, and g of x minus 1 is, so this thing squared. So we have, not this one, x minus 1 squared. Yeah, so if you want to, we can expand this as x squared minus 2x plus 1. Well, either is fine. But anyway, so this is the result of composing f and g. And obviously, this is, the result is, so if you look at this expression, it may not be so obvious, but if you look at this expression, we can see that this is always non-negative, always positive or 0. So therefore, it belongs to, the result always belongs to the set of non-negative integers. Okay, next let's prove one theorem about map composition. So suppose we have two maps, f from A to B and g from B to C. So we can compose f and g. So g after f can be made. And first, if f and g are both injective, then g after f is also injective. And 2, if f and g are, guess what, surjective, then g after f is also surjective. Okay. So let's prove this theorem. And to prove this theorem, let's go from part 1. And you have to understand what this means, okay? Remember what injective means? So this says if f and g are injective, so we assume f and g are injective to begin with, okay? Proof. So suppose f and g are injective. Then what does this mean? Okay, So that means for all elements A and A prime in A, if A and A prime are different, then f of A and f of A prime are different. Okay, so that's the definition of injection, right? So if f is an injection, then we can assume this. And same for B, same for G. Okay, for all elements B and B prime in B, if B and B prime are different, then G of B and G of B prime are different. Okay, so we can assume this also. Okay, our goal is to show that G after F is injective here. So now, suppose A and A prime in A are different. Then we have f of A is different from f of A prime because f is injective. Okay. Now, to both sides, if we apply the function or map G, then since they are different, then G of f of A must be different from G of f of A prime. Because these arguments are different and G is injective, so we can say that is injective. Therefore, but this means G of f of A means G after f of A. And G of f of A prime means G after f of A prime. Okay, this is the definition of composition. Okay, therefore, G after f is injective. Right? So we started from two elements that are different in A. Then we ended up two elements in C that are different by after applying G after F, right? So therefore, G after F is injective. So the proof is done. Okay, second part. To prove the second part, we need to understand what surjective means. Okay, remember the definition? So surjective means, let's say if we have set A and set B and we have a map F between them. So surjective means that everything in B had some corresponding counterpart in A. That, so for every element in B, there is some element in A such that f of A is equal to B. So that we can find such element in A for every element in B. Okay? So that's the definition of surjection. Okay, so since F is a surjection, surjective. So that means for every element in B, there exists some element in A such that f of A is equal to B. And so this is the definition, right? And G is also surjective. So that means, by definition, for every element in C, okay, remember G is a map from B to C. So the codomain is C, and every element in C, there exists some element in B such that G of B is equal to C. Okay, so we want to show that G after F is surjective. Okay, so this is going to be shown to be a surjection, right? So to start with, so g of f is a function from map from A to C. So we pick any element in C. So let C be any element. In C. Okay. So since G is surjective, there is some element in B such that G of B is equal to C. Okay. Now we consider this element G of B. Okay. So let's see. We have B and we have C, and for any element in here, there exists some element in B such that G of B is this one. Okay. Now, for this element B, so we can say that there exists some element in A such that f of A is equal to this element. Okay, but f is surjective. Therefore, there is some element in A such that f of A is equal to B. Okay, so this B is equal to f of A. Therefore, we have G of B or equal C is equal to G of B, which is equal to G of f of A, but that is equal to G after f of A. So therefore, for any element in C, there exists some A such that G after f of A is equal to C. Therefore, G of f is surjective. And we're done. Okay. So in this theorem, part 1 means if we have two maps, so from A to B to C, so F and G. So if two elements in A are different, they are mapped to two different elements in B, which are again mapped to two different elements in C. So if the sources are different, then the destinations are different. If F and G are both injective, okay? And if G and F are both surjective, then for every element, for every element in C, there is some element in A such that that which maps to that element in C. Okay, so everything in C is covered if F and G are both surjective. And from this explanation, I think it is quite clear that if F and G are both bijective, then their composition is also bijective. Okay, next we show that map composition is associative. Remember what associativity means? So let's say we have three maps. So f from A to B and G from B to C, say, and F, G, H from C to D. Okay. Then we have, if we apply F, compose H and G first, then compose that with F, and the result is the same as first we compose G and F, then compose H after that. Okay, so that means map composition. So this the operation of composing maps is associative. Okay, so that means how the order we apply the composition doesn't matter. Okay, I mean, of course, they are not commutative, so we cannot swap the order, but the order of composition itself is irrelevant. Okay, so first we apply F, then G, and compose them. Then after that we compose H. That is same as first compose G and H, then compose that with F. So after F, they are the same. So graphically, diagrammatically, we can express this fact as this. First, we apply F from A to B, and we apply G from G to C, and we apply H from C to D. Okay, then we can compose G after F here, G after F, and we can compose H after G here, H after G. Okay, so either way, so we can go from here to here, or we can go from here to here. They give the same result. Okay, so that's so that means this diagram is commutative. Okay, it doesn't matter how we go along the path. Okay, so let's prove this. The proof is actually quite straightforward. Just apply the definition. Okay, so first take this one. So H after G after F. So apply that to for any x in A. We apply this. So first apply the definition of composition. So this is one map and this is one map. We are composing these two maps here. So according to the definition of composition, first we have H after G of F of X. Okay. Now we apply the definition of composition to this composition. Okay, then that becomes H of G of F of X. Okay. Now let's consider this part. That is G after F of X, right? Then consider this composition. That is H after G after F of X. So for any x in A, we have this equality. So that means these two maps, these composed maps, are the same. So they are equal. H after G after F is equal to H after G after F. And we are done. So because of this associative property, we can just write this as H after G after F without parentheses, because the order of composition doesn't matter. Okay, it doesn't matter, so we can just omit the parentheses. Okay, finally we explain this important theorem, which has a tremendous implication. Theorem. Let alpha be a map from x to y. So x is a set, y is a set, and alpha is a map. Then the following two propositions are equivalent. Okay, 1. Alpha is a bijection. And 2. And there exists a map, let's call it beta, from y to x, such that beta after alpha is the identity map of x, and alpha after beta is the identity map of y. Okay, so 1 and 2 are equivalent. So that means 1 implies 2 and 2 implies 1. In other words, alpha is a bijection if and only if there exists another map, beta, from y to x, such that and this holds. Okay. So this implies that if we have a bijection, then we can define its inverse map that is given by this beta. Okay, so beta is a map that reverses the effect of alpha. So it's called the inverse of alpha. So let's see how we can prove this. Okay, so of course, again, in order to prove something, we have to understand what the statement says. Okay, so first, we are supposed to prove that they are equivalent. Okay, equivalent means 1 implies 2 and 2 implies 1. So we have to prove both directions. Okay, so let's first try this direction. Okay, that means we assume alpha is a bijection, then prove the proposition 2. Okay, so suppose alpha is a bijection. And that means for every element in y, let's say, there exists some x such that alpha of x is equal to y. Okay, bijection means it's both injection and surjection. So this property comes from the surjection part of the bijection property. Okay, surjection. Alpha is surjection. Okay. However, since alpha is also injection, this x must be unique. Okay, injection means no two different elements in x give rise to the same y through the map alpha. Okay, so x and y, if we have like this, if we have two different elements, this type of thing never happens for injection. Okay, if two different elements are in x, then they must go to different elements in y. Okay. In other words, so of course we are mapping through alpha. That means if we pick one element in y, then the corresponding element in x must be unique. There is only one element in x, such that alpha of x is equal to y. So this is unique. So in that case, we sometimes we write like existence and exclamation mark. Or sometimes we write like existence and 1. So this means unique. There is only one element such that alpha of x is equal to y. Okay. Now, we want to prove the existence of some map beta such that this and this holds, right? So how do we define this map beta? So using this unique x, we define for each element in Y, this unique element must be the value, the output of beta. Okay. Using this X for each Y, define this map. So this is defined for every element in Y, right? And this X is determined uniquely for each Y. Therefore, this beta is well defined. Now that we define a map beta, we need to show that show these two properties. Okay, beta after alpha. Beta alpha after alpha is equal to ID. So alpha is x, so it should be IDX, and alpha after beta is IDY. So what is this IDX? It's the identity matrix from X to X, right? So that means, so IDX is equal to X. So it gives the same X as its input. So for each element in X, and IDY means for each element in Y, it gives Y, right? So we need to show that this composition beta after alpha is equal to IDX, and alpha after beta is IDY. So let's show that beta alpha after alpha of X. So for each X in the set capital X, so beta after alpha is beta of alpha of X. So what is alpha of X? That is actually came from here. So we have some Y, but beta of Y is defined this way. So this X is the same as this X. So this gives X. It's the same X. Therefore, so this means it's equal to ID of X. So we are done for the for this part. And similarly, alpha after beta of Y for Y in the set capital Y. So that is alpha of beta of X, and beta of X is beta of Y is equal to X by the very definition of this map beta. Okay, and alpha of X is Y, and this Y is the same as this Y, of course. So therefore, this map composition alpha after beta is equal to ID Y, and we are done. We are done for this part. Okay, we are still in need to prove the opposite direction. Okay, so that means suppose such beta exists. Such means the beta that satisfies these properties, right? Okay, then from that we need to show that alpha is a bijection. So we want to prove that alpha is bijective. And bijective means surjective and injective. And injective. So we need to prove both properties here. Okay, so let's start from surjective. Okay, so let Y be any element from Y. Okay, then apply the map. Let's see which one was first. Okay, alpha after beta to Y. So from assumption, this is equal to ID y. So this is equal to y. And on the other hand, this is equal to alpha of beta of y. So this is a subset of the image of alpha, right? So let's see, x and y. We have x and y. We have alpha. So the image of alpha in y is always a subset of y, right? Image. So wait a minute. So this is the image of alpha. But here, for any y, so this is any y in the codomain of alpha. That is a subset of the image of alpha. So that means image of alpha. Wait a minute. So that is y is a subset of the image of alpha. But trivially, we always have image of alpha is a subset of y, the codomain. So we have this subset relation in both directions. Therefore, necessarily, so y is a subset of image of alpha, and image of alpha is a subset of y, so that means these two sets are actually equal. So that means the image of alpha covers the entire y. So that means alpha is surjective. In other words, every element in y has a counterpart in x through the map alpha. So the surjective part is done. And what's left is to prove that alpha is injective. So injective means, again, x and y. And if we have two different elements in x, then through alpha, we have two different elements in y. Okay. In other words, if we have one element in y that apparently comes from two different elements in x, then these two elements are actually equal. They must be the same point. Okay, so that's a contrapositive of the previous statement. So now suppose we have alpha of x equal to alpha of x prime, and x and x prime are elements of capital X. Okay. From this assumption, we show that this x and this x prime are actually the same element in the domain. Okay. So from this equality, apply to this equality, to both sides of this, we apply beta. Since they are equal, if we apply beta, they are still equal, right? But beta of alpha is composition, beta after alpha. So we have this, therefore this, beta after alpha. And by assumption, beta after alpha is equal to ID x. So the identity map on x. But identity means they just give the same value as the argument. So x and x prime are the same. Therefore, alpha is injective. So taken together with this result, therefore, alpha is bijective. And we are done. And it's actually easy to see that this beta is also bijective. Not only alpha, but this beta is also bijective. So as I have already explained, what this theorem says is that if we have a bijection, then we can define its inverse map, that is beta. Okay, and this inverse map, if for alpha, is usually written as alpha inverse. Okay, so if we have a bijection, if we have a map that is bijective, then we have its inverse that is usually written as alpha inverse. Okay, and that's it all for this video. See you later.